Good morning, everybody. Thanks, Laurie, for this introduction that, that I find very hard to improve on in whatever I'm going to say. So, I think the second day of a conference is always the good day to go with our head in the weeds after we got the larger picture out of the way the first day. So I hope you don't mind that I'm going to talk about mostly the work that I've been doing and that the whole community has been doing, and take you on a journey to what I have tried to solve with this work and how I see the future develop in answering some hard questions that we have about model fidelity. And it is model fidelity that is the leading theme of my presentation this morning, because we have quite a bit to say about how good our models actually are for the things that we're using them for. And what better way to start than with the quote from good old George Box that all models are wrong, some are useful. And that sets an important tone because we're working very hard on still extending functionality and fidelity, and I sometimes feel that we're more focused on functionality, as maybe we should, than on fidelity. Fidelity means that we're going to go with every corner, with every term that we take, we ask ourselves, are our models good enough to do what we're using them for? And so some soul searching will tell us that, well, are we really well served by the tools we use, or do they need to be more accurate? Do we need to go to a higher fidelity? So when is a model really good enough? Do we have a way to inspect that? And then the more philosophical question is, do we need to be accurate in the first place? And you know that I'm already leaning towards bombarding you with some work in uncertainty analysis, and that is really coming out of the question, does it help if we know how wrong we could be in the predictions that we make? And so that then becomes an important way to approach fidelity. Fidelity from the side of, well, if we know how far we can be off the target, then obviously the fidelity doesn't meet the expectation. But the bottom line is really, with whatever we do, and we talk a lot about that amongst ourselves, I'm sure, is there a payoff of this modeling work in industry? If there is not, then probably there's not a good reason to strive for higher accuracy and higher fidelity. But there are three different questions that we can ask about fidelity. First of all, how accurate? So does the model give the correct answers? Then the second one is how valid. It's a very different question because the validity of a model can only be inspected by checking whether people make the right decisions after using the model. And then you can answer the question, well, how relevant? Does anybody care? And I think that for our discussion, we need to deal with these three questions separately. And so if we only stick at the fidelity, for higher fidelity, more accurate models, and forget about the next two questions, we really don't achieve very much. So how do we check these? How we even come close to giving answers to those questions? Well, the first one is uncertainty analysis. I think it's a good tool to find out how wrong you can be when you make a prediction or an assessment. So that's probably is a good vehicle to answer the first question. The second question is already harder. You have to run experiments with decision makers that use our tools and see how confident they are in making decisions. And then the hardest question to answer is, well, can you quantify what society really achieves in adding value by using our tool? And that depends on how you then identify best decisions based on our work and how you evaluate the outcome of that. Hardly anybody is doing that because it's so difficult. So, one step back, let's see what we did previously. So this doesn't come out of the blue. We cannot just say, okay, uncertainty analysis is the key to everything. We tried other things before. So just to sketch what we're trying to do, we always start from a design model, some idealization of something we want to realize. And short of its realization, we turn this idealization in a computational model, some differential algebraic equation set. And in the past, we said, well, if we can realize the thing and measure it and predict by computation, we can compare the two and we have some measure of correctness. And that's what we did in the 80s, 70s, 80s. And that's still very valid to go back to that work and see how we did things at the time. And we found soon out, well, we only realize everything one time, so it's very hard to generalize any findings of this correctness. But even worse, if it's not correct, it's probably the effect of many compounding effects, and we cannot separate them this way. So we soon came to the realization we need to do something different, but still quite elementary. And so starting from the same thing, now we said, well, wait a minute. I know that there are certain things like the efficiency of a solar panel, the conductivity of a certain construction, U values, internal mass, ground reflectance, and we probably can come up with some assessment of the uncertainty that lies in these parameters of our model. And then we do an uncertainty analysis by propagating all of these identified uncertainties through a little engine, a Monte Carlo engine, non-intrusive use of our simulation tool that just runs over and over with different sampled values of these red dot parameters. And then by recombining the outcome of all of these samples, we construct a distribution over the outcome. In a nutshell, that seems all nice, but I've been saying for quite a few years that, the garbage in, garbage out hasn't vanished. We just now have quantified garbage out. And that sounds like a pun, and it is intended to be, but there is some real truth in it. I have done myself, and I've seen others do these early attempts with little else to show for it than that we had indeed garbage, but quantified. So some historical perspective from everything I have tried to read from the early days. It all started with Kevin Lomas when he started working on his sensitivity analysis, soon followed by Ian McDonald. I don't think anybody here in the room does work on uncertainty analysis without referencing him, and rightly so, supervised by Joe Clark at Strathclyde. I think Ian is rightly viewed as the first student working in this field, soon followed by Stan DeWitt, who I had the pleasure of supervising. He did something similar at TU Delft, where I was at the time, but focused more to the decision making, so already making this first step towards, well, uncertainties are meaningless unless you can do something with it, and unless you show that there is relevance of knowing these uncertainties in what you do afterwards. Stan also had another little claim to fame. He said, well, all of these parameters that Ian already did, I don't have to do, so I'm going to focus on a couple of difficult ones. And he found out that we really don't know how to quantify the uncertainty in many of the parameters that we use. So he ran into Roger Cook, one of these unique people that inspire you for life, American at the time working in the Netherlands, came as a jazz musician to the Netherlands, did a PhD, and became this famous guy in statistics. And he has the quote from that time that I still remember: even if you think you don't know anything, you know more than you think. And that's important because he built his whole career on finding ways to elicit things from experts that can be translated into hard-coded sources of uncertainty. And So I have smart Alex students sometimes that think that they can only also take this around, and they come and say, well, professor, you gave me a D. You think I don't know anything, but really, anyway, you know how it goes on. So what happened since that early period with the people I mentioned? Well, here you see just a quick scan of many people here in the room that have worked in this field. And I'm really so excited about this, to see that since the late 90s, early 2000s, so many papers, so much useful work has appeared. And probably from this conference alone, I will have to add 30 names to this list next time. So what have we learned in those, let's say, since 2002, since these two PhD theses appeared? Well, quite a bit, I guess. So we still have the rudimentary uncertainty analysis, the way we always do it. We have become better in quantifying the uncertainties that resides in these parameters that we only know in a sort of imprecise way. But we also have come to realize that there's many hidden discrepancies in the models that we use. They cannot be exposed as parameters uncertainty. So this is one of the important realizations that I had to go through, and once I realized, guys, stop doing this, because when you try to locate model discrepancies, so parts where the model is just not using the right physical model, or a reduced order model for certain physical phenomena, trying to export that in parameters that are exposed to the input file is futile. It won't work. So we call this model form uncertainty. Most of the statisticians call that model discrepancy. So it's very important to identify these green dots. So that has been the recurring theme in a lot of the work of the last 10 years. Another thing which has always been there but has become really, really emphasized recently is what we call scenario uncertainty. And of course, the first thing you think about when you think about scenario uncertainty is, how do we use the buildings? In other words, what do the occupants, or according to Ray Cole, I have to now call them inhabitants, what do they do to the building? And we will come back to that later. So we then have, every good thing in life is three. So we have these three major sources that we can now cleanly separate. We have model parameters. Think of it as our way of specifying the imprecise physical knowledge. And it's somewhat improving, as we learn more, as we study more, we can take away some of that impreciseness. Then we have model discrepancy. This forces us to go inside the tool and seed uncertainties in the tool. The green dots cannot be exposed to the outside. So in a Monte Carlo way, they cannot be used in a non-intrusive manner, simply rerunning the same simulation. You have to go inside the tool and seed something in there which captures your discrepancy in the model. And then we have scenario uncertainty. The important part there to realize is, and I don't think enough researchers do that, according to my view, that we have to realize that is totally orthogonal to the uncertainty quantification of the parameters. And my professors always told me, never add two things that are orthogonal. Just because you lose a very important piece of information, you lose that, in fact, they are orthogonal. And once you throw everything together, you lose that. It's like the coffee and the milk. Once together, you can't taste the coffee anymore. Good. So that's where we are right now. And I think you see different groups working on these three different major categories of uncertainty. It's very good. They all have their own little dynamics in which they proceed. So a little bit re-examination of the fidelity issue here. So you see the model. We have an input. Oops. We have an output, y, and we have a model formalism with inputs, x, and parameters, theta, and then we have a structural error, usually also as an algebra over the inputs and the parameters. And so what we're doing, if we're cranking up fidelity, we're basically working on the right side of the screen here. I noticed that my cursor doesn't work, so excuse me for that. Otherwise, I could point you to the right side of the screen. We're going from this, where we're trying to make the structural error as small as possible. And every step we take in becoming more precise in the different parameters, we take the structural error from a very fat distribution to a skinny one, and ultimately an anorexic one that then has limited to a very small distribution. And so once we take fidelity from the perspective of uncertainty analysis, this is really what we're doing. Cranking up fidelity means that we try to make the structural error as small as possible. And that is being as precise as we can in all the other categories of uncertainty as well. So was it an easy job to get to the point of quantifying uncertainties in all these parameters? Because that's the first thing you have to do. It's not sexy. It takes a long time, but it has to be rigorously done. And so we set out to do it. And we used all of the work that collectively is produced by this group. And so we were constantly, with my group of students, scouring for newer papers that had been published by you, basically, to say, well, what is in there that we can use to quantify another source of uncertainty or a better model that was published, reducing the uncertainty in some parameters. And that's how we went from scale on the urban and microclimate level to the building envelope material level, to the HVAC system level, and finally to people and process level. And so that was already a nice way to categorize it in these different scales so that we could structure the work that in all of these scales we have a separate set of parameters that we needed to. Parameters and model form uncertainties, so modules that capture the discrepancy on each of these levels. Painstaking work. We have published many papers about it. I don't blame you for not reading them all because you thought probably, well, another paper that says that we did this work and we came to a quantification of this discrepancy. And it went from, in all, some 40 plus parameters and 11 model discrepancy modules. Only one thing is still missing, the Waterloo, basically, of the work that we have been doing, and that on the HVAC level. I don't have time to go into that. It would almost be a separate presentation. But if you want to talk to me about that, I'm really looking for volunteers to take this on and help us make a major contribution to that field. It's the longest last mile, so to speak, of uncertainty analysis. So what has this all amounted to? Well, we call it the UQ repository. So it is the collective work of all of us brought together through a rigorous statistical analysis in a repository that we produce in the form of an Excel spreadsheet, but also an XML file. The latest work that we've done is we produced the GBXML UQ schema, which lets you, if you have another simulation tool, which lets you use our UQ repository as long as you have a GBXML parser, so that your simulation can run with a GBXML instance file. As long as you have that, we can ship to you something that regenerates that and automatically samples from your building model and infuses all the uncertainties from our repository. Is this enough? Well, clearly not. Since the early days, both in Ian's and Stan DeWitt's days, we said, well, There is no such thing as a generic uncertainty analysis, but I still have to bring it to the front of every new PhD student when they're doing that. Every case has a different set of uncertainties, but how we try to do that is we start from a vanilla set and then do a Yogli-Mogli fashion topping and different flavors. But the point is, if you try to do that, there's no expertise to do that. So I work from my vanilla UQ set of all the parameters with their distributions as identified, so all this painstaking work. But then I look at the specific building, and I need to color that in some way. Maybe in that building, the infiltration, based on the type of facade, the range of infiltration uncertainty is much smaller than the vanilla set. But how do I decide that? So a lot of things still need to be worked out to see how can we instruct a modeler to transform the vanilla parameters in the specific building. And so we've been playing with several ideas, going back to the old expert judgment study, Roger Cook's brainchild, or maybe do that in a more informal UQ charrette way. This is still hanging out there. For now, I think we're all pretty content to at least do this first stage of vanilla UQ propagation through the model. Here you see the modules. So all of this work that I just showed is basically not related and is independent of the typical simulation tool you're using. This, however, is very related to it, because what you're really characterizing here is the discrepancy in the particular simulation code that you're using. So obviously, if you use another simulation code, all of these modules will take a different shape, and some modules will disappear and others will pop up. This list, so we tested all our work on Energy Plus, so we built this list for Energy Plus. 11 modules that characterize some discrepancy in the way that Energy Plus currently does its calculations, its simulations, and the way it forms its algebra in the different modules. Don't forget what I said. So this cannot be infused in the analysis without breaking open Energy Plus and reprogramming certain parts in there. So this is all based on recoding and recompilation Energy Plus, as you would have to do it if you try to emulate this work for another simulation tool. Something I haven't talked about yet is how do you then propagate it? So is there some mystery in the workbench? Well, not at all. As long as we're doing this non-intrusive propagation of uncertainties just by sampling and pushing it through the workbench, anybody, any clever PhD student can write code that does basically this. You have some uncertainty categorizations from your UQ repository at the start. You build a nice little sampling engine. You sample from all of these distributions. You put it through your input file, run the simulation, and at the back end, you recombine all the outcomes and you generate an outcome distribution. We use, in this particular instance, and I frankly think there are, in terms of computation, better engines on the market, but we use a model center to do some of the mechanics of the Monte Carlo engine. You don't need to do that. Program it in Java, and you probably have less difficulties in proliferating what you do, because now everybody has to buy this terribly expensive model center tool. Unless you're an academic in the US, then it's for free. So cloud, of course, everybody's doing lots of things in the cloud, and of course, there are lots of cloud cowboys now around. They don't want to be bothered by the discussion about fidelity, which I understand, and so they're working along their own dynamics, unstoppable, I might say. And so we, of course, also, to limit the load on the computational time, we also use the cloud. Okay, So although there are many engines around, I always look at an engine as, does it a couple of tricky things that you really need? And that's the only thing that I'm usually interested in. Like, does it do batch sampling? Batch sampling is something that I can explain very easily. If you have a building with 10 windows and you say, well, the U value of a window is uncertain, make sure that you sample in a way that not all windows in every sample have the same U value. This makes no sense. You know, think of the windows coming out of the factory. They all have different U values. If you load them on a truck, drive them to the site, they are randomly installed in the building, and so you need to sample what we call batch sampling, reflecting the fact that all of these are separate instances of a class of uncertainty, not all having the same uncertainty. Then there are all kinds of pre- and post-sampling methods that you can use for retrofit studies. Don't forget that in a retrofit study, you only touch a part of the model. The other part of the model that is untouched stays the same pre- and post-retrofit. So you need to do some clever tricks there that if you compare the improvement of the retrofit, that you do the proper pre- and post-sampling matching. And then on the sensitivity analysis, which is a very intrinsic part of any uncertainty analysis, you have to do some special things. If your parameter set is very large, you have to have a good screening algorithm, Morris, for example, and then you do a sensitivity analysis with something that is probably more adequate than Morris. But it's not relevant, it just is something that you need to be aware of. That you don't forget to build these little functional nuggets into your engine if you decide to build your own engine. Then something that I deal a lot with, or from time to time, that a clever statistician wants to work in buildings. They know how to do all kinds of clever things with propagation, and there is an intrusive way, so throwing away your Monte Carlo engine and doing another method which is called polynomial chaos. And that is for, going back to the formula, that's not a real mystery. What you do in that case, that is that you not only develop your Y, your outcome, over space and time, but you also now develop it over the uncertainty distribution. So at every point in time, a certain parameter Y has an unknown distribution. And if you think of finite elements, you could develop the base functions in space and time and combine that with certain polynomial functions that approximate the distribution at every moment. But if you try to do that, you are going to be probably very elegant in solving the whole equation. You have to totally rewrite Energy Plus, or whatever tool you're using, by the way. And my final word on this is that don't even try, because I think we now have enough proof that for high dimensionality problems, this is just not worth your effort. And if you don't take my word for it, read Tony O'Hagan's paper, which floats on the web. It's called Polynomial Chaos Tutorial and Critique. It spells out why basically you should not do this for the type of problems that we're facing in buildings. Okay, right, I think on cue, we have the groundwork done, and we can go out and start working with these questions. So I hope I have made a plausible case that a rigorous uncertainty analysis is needed, or at least a good instrument to start inspecting model fidelity. Okay? So if you object to that and you think I have not built that case, let me know. Then I probably have to give the award back to Laurie. Not yet, she says. She wants you first hear the whole talk. Good. First question, simple one, to start simple. Is uncertainty analysis the road to higher fidelity. So does it help us to, over time, with this community here, find out what we need to do to come to more accurate, more appropriate tools, or maybe decide that our tools are good enough? I think that here we're not really different from any discipline out there. Every discipline is inspecting how good their tools are. They're using uncertainty analysis, similar to what we are doing and proposing here. And it's really a no-brainer to say, well, uncertainty helps you to understand not only when or whether we need to make improvements, but also helps us to understand where. So it helps to identify those discrepancies or those parameters that have the highest impact on the error that we have, on the potential error that we have at the end. So this is a yes. Okay. This is why we're doing all this work. It should be not a debate. Second question. Will uncertainty analysis close the performance gap? So that is a question that I have been seen discussed in many groups. And it's one of those items where either you want to participate in this group or run away, because you can't just not stomach the unstructuredness of the discussions about that in many cases. First of all, what is the performance gap? Well, we all know that. Many work published that say, well, if you compare what we predicted and what we now measure, we have a huge gap. Fine. Maybe it's unavoidable. Buildings are the last known engineering product made by hand. So maybe it's not all that surprising. But then I think what we lack is a good discussion of what the performance gap really is. Because it's not the model only. So if we start from design specs and we say we turn that into offer that to a model and the model generates a prediction, yes, we have talked now for 30 minutes about the model uncertainty that handicaps us when we go from a spec to a prediction. Fine. And we can probably now characterize the error in the prediction pretty well based on model uncertainty. But look at all the things we have. First of all, realization uncertainty. We have really no clue how close the realized building is to that design spec idealization. But not only that, once we have the building realized and we take it into use, we have all these operational and usage uncertainty. And I'm not talking about only occupancy. Occupancy is just a thin sliver of this. This is how the technical people, how even the organization that occupies the building, how they are dealing with this building. And we have, of course, faults and detection, faults and deterioration that we simply push to the detection guys. So we could say, well, this error should be small because there will be a regular update of this building that catches these. Not sure whether that is the case. And then we have measurement error, so that even the things that we measure are not, per definition, totally correct. And then we say, okay, now we have predicted and we have used, and now we have this definition of the performance gap. And so this is the whole picture of what we're dealing with if we're talking about performance gap. So we now realize that there are some really big gorillas in the room that impact, first of all, the workmanship. This is not just that we don't know how a building is going to be realized from the spec, so how good our idealization was. But also, in the daily operation of that process, a lot of things intervene that may not even follow the way you thought it was defined. And so that's workmanship issue. But then another gorilla in the room is the modeler's bias. So how good is the modeler in turning that design specification into an input file for the model? So looking at all of this, I would say the question about is uncertainty analysis the right way to close the performance gap? Hell, no way. So we should be clear about that. So let's be a little bit more modest. Does our work identify the role of the model in the performance gap? Well, you are now thinking, okay, so he modified this whole thing now that we say, okay, that we can do. But even that is not so proven, because I would have to see the proof that for a set of realized buildings, our uncertainty analysis, closing all other sources of uncertainty, now predicts the right outcomes for those buildings. I haven't seen any proof of that either. So a couple of years ago, I found a student that was really interested in this, and he set out to do that. So he took selected a building set and did everything he could to rule out any other source of uncertainty. You have to read the thesis to see what kind of gimmicks and workarounds he had to invent to do that. And then he created models from the true building, because these were existing buildings, but mimicked them as if they were design specs, but now design specs that rule out any other source of uncertainty. And he used a very interesting technique, used our vanilla uncertainty, the model form, and the scenario uncertainty, and then used a technique called PIT to say, okay, can I find the proof that once I have eliminated all these other uncertainties, that our analysis now predicts what is actually happening in this building? And for the 6 buildings that he chose, he came up with this proof that it is. That's why I'm showing you these curves to the right. The closer you get to this uniform CDF, the more reason you have to believe that you're doing well. And so he provided this proof. This is only one proof for a hand-selected set of buildings, so it may not mean that much yet. But it is definitely better than that our first major test would have proven that we are not there yet. So this is a yes. Okay? Does uncertainty analysis improve confidence in our predictions? Because I've heard many of you talk about, well, and not only you, we have friends in high places that say, well, building simulation, that's plus or minus 40% correct. Well, that doesn't elude a lot of confidence. So the philosophical question there is, if you confess to ignorance, are you then more confident? No, it's a funny philosophical question. But there are actually people that think about that, especially political pollsters. They ask somebody, well, how much do you know about politics? Well, not much. So who are you going to vote for? Or I'm absolutely going to vote for Donald Trump. And so this is one way of saying, well, my ignorance obviously doesn't hamper my confidence in making the right choice. So in that sense, the answer would be no. But on the other hand, even a skeptic will gain confidence if he knows that from an uncertainty analysis, I will not be more wrong than 15%. I mean, this can be helpful, right? You make a prediction. You do the due diligence. You hope that the big gorillas of other uncertainties are no longer in the room, and you say, well, what I find is this distribution, and I can give you a guarantee that you're not going to use more energy than this number. So I would say I see both sides of this discussion, so I give it a tie. I don't know. I need to learn from you whether you sit more on the yes or the no side here. Okay, this is a hard one. So does practice benefit from uncertainty analysis? So I hear people complain. What we do, is within our academic community, we elevate the level of our work, and it's clearly visible how much we have progressed over the years. But what about practice? What message do we have for practice? Does all this work, in this case uncertainty analysis, but probably extends to other work that we do, does that give a quantifiable benefit for practice? Well, the one thing I want to say about that up front is that if you think that practice is interested in our quantification of uncertainties, forget it. Okay. For two reasons. First of all, they don't know what to do with it. Actually, they don't hardly know what to do with what you give them now. One deterministic outcome. So what do you expect they will do with that you give them a distribution? Basically, admitting your incompetence to give them this one number. That's not going to help. But there's also another reason that I always say uncertainties are basically meaningless. There's no real life, no real, reptilian feeling interpretation of uncertainties. So we need to go to risk. And, there are many cases now floating around where we know that maybe by a better risk analysis we could have avoided some disasters. For instance, you built this perfect building in San Francisco. You say, I don't need a mechanical cooling. You build a totally unnatural ventilation. You take the gamble, so to speak. And it's clear that that is a case where you could have done a risk analysis and, for instance, calculate the probability that the hours of discomfort greater than 150 occurs 5% of the time. That translates really to the risk that 1 in 20, your building will lose X% in productivity if you can translate discomfort in productivity loss. I think an owner can deal with this. An owner can think, well, if you give me that risk, put in a mechanical cooling. Maybe. Or, another risk measure could be, what is the probability that your discomfort hours will be more than 200 hours per summer? And what if the probability is larger than 5%? That would be that 1 in 20, you probably face the risk of litigation. That is something where it no longer becomes, I don't know what your uncertainties mean. Now it becomes, I know what that risk means. I'll be in court and fight an occupant organization that accuses me of producing or giving them a bad place to work. So that is basically, I think, the beginning of a message that we can give to practice, that our uncertainties help us to quantify risk measures that are meaningful to make decisions in practice. But still an uphill battle, because if you look at theoretical risk and actual risk, there is no credibly established way to do that. In structures, yes, I know what it means that if somebody tells me there is a 1 in 20 chance that in the next tornado or next hurricane your building gets flattened to the ground. I know what that means. These structures guys, they have it easy. They have limit states. We don't have clearly defined limit states that are already, adopted in practice. So we have a hard time coming up with risk measures that people can relate to those known damages, known disaster effects. And then we have another thing to deal with, that this is not just true for practitioners. No, it's not meant to be a practitioners there. This is everybody. Our brain is just not wired to act rational about risks. And there's lots of work done out there where we say, well, how do people make decisions with risk measures? And we all know the examples. And people make consistently the wrong decision. So this is something we also have to deal with. We provide them the risk measures, but practice will not see any benefit from it. So that's why people are working on these axiomatic utility theories, where you actually take out the reptilian brain of the Homo erectus brain of the early apes and make it a automatic decision engine. But then, why should humans accept that? So I don't think that's a very promising direction either. Okay, I haven't yet given this a yes or a no, because I wanted to make sure that we all understand there are so many areas where we make risk-conscious decisions related to energy, starting with the energy savings performance contract. But then there are power purchase agreements. You can read through the list. There are so many, usually investment relationships, where there is one party that signs a contract with another party, and somewhere in the contract there is a link to predicted savings. And as long as we are not sure about what the predicted savings actually will be, then we have, of course, to deal with the fact, how can we help these two partners that nevertheless want to sign a contract to make it transparent what the risks are for them. And so we are on that path. I think uncertainty analysis is definitely the step towards that, but we just don't have the proof and the work to prove that we can get to the point where the rubber hits the road and actually study the making of these contracts in practice. We have done it in one case, and the paper will soon be published, and the student who's doing that work is here, energy savings performance contract, where we show that the guaranteed savings amount, if you're familiar with ESPCs, this is something that two partners decide on, that actually in current decision making, that guaranteed savings amount, so that amount that you pay every month for the upfront costs for the retrofit that somebody else has financed, that actually current decision making about that amount of money is poor. If we would build an engine that translates risks into that decision making moment in time, we could get to an outcome that is better for both parties. So this is the clue here. Everybody wins. And so I think that one case where we believe that we have a proof that everybody wins is not enough to convince practice. So this is both a yes and a no. Then there is a little other, this is going to be tricky, this little exercise that I'm doing here now. There is this one thing that we try to say, okay, can we get the larger community, practice included, on the same page with what uncertainties mean? And so, well, did I mess it up? Yeah, it's this one. Is it that one? Got you. Thank you. I did mess it up, but not that much. So we built this little website, and here you see a glimpse of it, our first attempt to come up with a projection, an image of all the uncertainties related to certain types of buildings. And you see here to the left how we chose all the 16 reference buildings from DOE, from the commercial reference list. Here we see the different sensitivity indexes that happen when we choose a certain output type. For instance, zone heating demand. We choose a certain climate zone, and we see for that heating demand, for that type of building, these are 200 samples that are sampled over all of the distributions of the different parameters. And we can now select the different sensitivities. You see how these points move is because we keep the sample identity intact if we produce the outcomes in a different way. We can go to other system heating demand, see the same samples here against the, I think this is the ELA per external area, which is the most sensitive parameter here. We can go for other parameters, and we see how the sensitivity of the parameters decreases, of course, and we also see how the different samples are distributed over the domain. I have to scroll down. You know, the image is a little bit messed up. It seems to be that we have a very old browser here. this didn't help at all. I better leave this. So you see what we were trying to do here, create a mess, apparently. Okay, and so we try to find out, okay, when we are going to do this with a group out there, and we present something like that, showing how seeded parameters from a set of uncertainties go into the outputs of all these buildings that they know. Those are the reference buildings, and we thought that people would like to play with this. And we went to certain funders, to certain people with money that we thought would be interested in this, and we got very interesting reaction that I can only summarize in one picture. And that is, and if you think you recognize the last person that reviewed your grant proposal, you may be right. And so this was funny because you see these smiles of, hey, this is interesting, but no. So this is a no. No, it's very hard to get any traction with the outside world to say, well, this is what our uncertainties mean. Okay, another question, and here I'm going to be a lot more positive, so already I tell you this will be a yes. So can we pick real winners? And I was looking on the web yesterday for a good example, and I thought, well, why not take driverless cars? You know, there must be alternative technologies that achieve the same, what Google is trying to do with their driverless cars, and I came across this picture. And I thought it was actually a very interesting other idea of a driverless car. And so, seriously, what we are trying to do is, can we make a true distinction between different competing technologies that, based on a pure deterministic analysis, we would not be able to see? And the examples here to the left are very clear. You know, if the red one is your deterministic prediction, you can have two different situations. One is where your distribution and your deterministic prediction are pretty close, and sometimes even the deterministic prediction is the median value of the distribution, sometimes totally outside of it. And you can never predict that, so that's why it's always good to subject the technologies that you're comparing to this analysis. More common is that you find these two situations to the right, where you have two options, the blue and the red one, and you see that in the first case they're hardly, I wouldn't know which one to choose there. There's really no distinction between them. To the right, they have the same median value, and so on a purely median expectation, you would not be able to choose. But now you see that the one distribution is much skinnier than the other one, which means that the behavior in the tail of the red technology could be the differentiator between choosing the blue one or the red one. And I've always been inspired from the very early days that we did this work by a theory by George Akerlof that I once stumbled over. And he came up and got the Nobel Prize for it with this theory about asymmetry of knowledge. And so his theory was that if the buyer and the seller of a used car have asymmetric knowledge about which car is a lemon and which car is a good car, then he proved theoretically that the used car business would go broke, would vanish. Because at a certain point in time, there would be no used cars sold anymore. And so the corollary of that is that everywhere where you restore symmetry in the information between two parties, you will benefit, because the market will survive. So wouldn't it be nice if we could now project this theory on the market of retrofit financing? Yesterday's keynote speaker said that in India, But he obviously knows very well that this is not just an India problem, this is everywhere, that there's so much money on the sideline that is not going into retrofit, obviously because the financial mechanisms don't recognize retrofit as a market where you can make money. And so our theory would be, okay, well, wait a minute, that we know the reason for that. There's asymmetry in this market. Well, you don't believe that, right? That would be the reason. Well, it is not the reason. There are many other things why the money is not coming off the sideline big time. So and that's why governments and many other institutional funders still have to push this market to get going. So we should definitely not overplay our hand, but I believe that it will be important in the future that we can make an additional contribution to that in restoring symmetry in the market. By the way, you know why the finances doesn't work. If you walk into a bank and you say, I want to borrow this amount of money against the collateral of future energy saving, they kick you out the door. There are some enlightened banks that are now specifically chasing that kind of investment opportunity, but it's still a very small minority. So it's not so much the asymmetry in predicting the saving, but it's just the idea of borrowing money against the collateral of saving. Okay, nevertheless, I think I want to be bold here, and I think that we have a contribution to make in restoring symmetry through our uncertainty analysis, especially to pick winners among competing technologies. Okay, question 7. Does occupancy modeling add to fidelity? Okay, this is a tricky subject, because we're really dealing with a very special case of uncertainty here. This is uncertainty driven by ignorance. Because, why wouldn't I know what's going to happen in a building? Occupancy, presence, what people do in buildings, what kind of appliances they use, how many hours the light is on. If I do due diligence for the commercial market, for domestic it's different. But for commercial market, I should be able to come pretty close. Based on the design brief, based on the tenant organization, I come pretty close to predicting what the scenario of use of the building will be. And so to make it clear that it is really ignorance driving uncertainty in scenario, we made this explicit curve to identify, okay, perfect knowledge, which you never have, but just for the sake of the argument, that you would know exactly at every hour who is where and doing what in the building. And then there is the other extreme, you have total ignorance. Now, total ignorance is not really total ignorance. I mean, you at least will know how many desks and seats there are in the building and stuff like that. So let's look at total ignorance as you know the number of people, density, and you take the ASHRAE diversity profiles, because you have nothing else to choose from. So that would, in our case, be total ignorance. And you make that explicit. So I think there is where we need to be more specific in, if we do scenario uncertainty, what do we base this on? This is not that we don't know, or it's hard to know that a person does what. No, in my view, that's not the case in commercial buildings. So we choose to not know, and that's ignorance. So based on that, we came up with another important item in this whole discussion about occupancy, and that is that I would say we need to treat direct and indirect consequences of occupancy very differently. There's so much work published showing that occupancy has this huge effect on the energy use of buildings. But then you find out that 80% of that is just people putting electricity devices into sockets. Has nothing to do with the building. Okay, so that goes straight into the grid, straight past the electricity meter. And so there is no uncertainty analysis at stake here. I can calculate, based on what you assume that the lighting appliances, etc. are, I can calculate immediately without any uncertainty what the effect of that ignorance is on the electricity use of the building. But then you have the indirect use. So let's look at that. Maybe that's the big reason why we are so hung up on studying occupancy. How much more cooling energy will you have if you are not certain about the number of people in a space? Well, we did that at different levels of ignorance. So the blue one is the perfect knowledge one, which you never have. But for comparison, we produce it here. The red one is an approximation that doesn't have that much knowledge, but gets the averages more or less right, but knows nothing about the variability. So all the stochastics are totally off. But you see, you're extremely close. So all the jockeying that you did to generate these stochastic profiles don't pay off. Then there is a third level where you have total ignorance. And that's way off, but most of that is, as I show on the next slide, so now you're not even sure about the mean, but the mean is way off. And the mean is way off means that, of course, yes, you have consequences in the cooling energy that you use. So we studied that part a little bit deeper. So here you see them again. And then we said, well, if I know what the efficiency is of my cooling system, my COP, and I know what the mean additional heat load is from the people in the space, I could have calculated that and subtracted that part that I already know, for which I don't need a simulation. And then we find this little black dotted curve so close to the blue curve that we say, well, an uncertainty analysis was not necessary to do any of that work. I know that I'm doing this very fast and it's probably not very well structured, but you can read in a paper soon how we dissect the different elements of this scenario, occupancy, uncertainty, and try to one by one reflect on them and find out that it's really not a contributor. Now, do we sometimes need stochastics in certain instances? Well, we came up with one. So if you look at the power duration curves, where you're interested in how many hours in the year will a building use power above a certain level, which is only in these, very peak hours, yeah, you will see that the blue and the purple are way apart, and you need prediction, which is the green one, which gets the variance, so the variations also right, before you find a good prediction to the perfect knowledge one. But it's one of very few instances where we find good justification to focus so much on occupancy as a driver of uncertainty in energy use of buildings. So that's a no. Okay. Can uncertainty analysis lead the way to better tools? Well, absolutely. So, no-brainer, I would say. This is basically what it is made for. So if you look at the sensitivity analysis, you have all these parameters, maybe interspersed with a couple of model form uncertainties. By the ranking, you see, well, when does it become relevant to try to chase that discrepancy of model form uncertainty module 2? Well, hardly worth the effort if you haven't done anything about the much bigger sources above it. And even model form uncertainty 1 could be a candidate that you only tackle after you have ascertained that there is no way, or there are ways, to reduce the source of uncertainty in these other physical parameters. So when we make those decisions to pump money into model improvements, fidelity improvements, I think we should also always be looking at this. Once we're on the subject of sensitivity, you also see here, I think the slide should have been 2 slides up, but you see that occupant presence as a source of uncertainty for this effect on cooling energy is really in the low ranking. So this already would show you that the funder, the one we met earlier with the smiling face, would probably have to rethink all that money they're pumping into occupant presence research when you look at it as increasing the fidelity of my predictions. There may be many other reasons to pump money into occupant research, and certainly on the domestic front, slightly different universe exists. But okay, the answer is yes. Uncertainty analysis leads us clearly to the way of what to focus on first. And it also, I haven't worked on that a lot in this presentation, it also shows us how one tool can be compared to other tools in the ranking of their parameter uncertainties as well as their discrepancy in the different models. Okay, only 2 more questions to go, and 1 minute to do it in, so I'll have to speed up. Can uncertainty quantification improve energy codes? Okay, 2 answers. In spirit, yes. There was a time 10 years ago that I thought, wow, you know, if we go into a reward and penalty system for energy codes, people should really be penalized when their building overconsumes. Maybe not the occupant, maybe somebody else. But you cannot do that with a hard threshold. You know, there's so many uncertainties. So you should say, well, only if you use more than the highest 10 percentile of what I predicted, then you're doing something wrong. Then you will be penalized. But boy, I was totally wrong. So I've come totally back from that thinking, because the more you throw simulation, and then simulation with an uncertainty analysis at a thing like code compliance, the more you lose sight of the real target with codes. Codes should be simple, should be easy to satisfy, because basically all the work we do on code satisfaction is non-value added work. I don't know what good it does to anybody. You just have to pass that building. So, in fact, for codes we want less, not more modulus bias. And so I think the road is open towards normative calculations, simplified, reduced order calculations that will replace ASHRAE 90.1 and its lead incarnation altogether. And I think I find more and more people that are in agreement with that. Now, but I find very little proof that it is actually going to work. It's probably not going to work, but for other reasons. But it should work based on some of the tests we did. For instance, we put a test and said, well, you have normative versus simulation. Yes, the simulation tool it takes a lot of issues on board in a certain building than the normative tool gives credit for. So you have quite a lot of outliers. It's not on this perfectly straight line. But then you do another test. You say, well, I don't care what the outcomes are. Coding is really about ranking and comparative analysis. So what if we rank the buildings from best to worst with simulation, and then we rank it from best to worst with normative calculation? If the 2 rankings are similar, or maybe even identical, why should we do the simulation-based approach? And so we published this paper in BS 2013. And we found very good results. The Wilcoxon test on ranking similarity passed with flying colors. And then we did another thing. We said, well, assume that you have in the simulation side a little bit of modulus bias or other sources of uncertainty so that you get 15% of uncertainty on the outcome. On the normative tool, if under all ideal consequences, you would always have 0%. That's the benefit of the normative approach. Whether in the current tools that is actually maintained, no, but that's another debate. We should just make the normative tools better. But here with 15%, we already find that the misclassifications So the dissimilarities between the two rankings would already go into the favor of the normative tools. So no, I think we should not chase uncertainty analysis for coding purposes, code compliance purposes. Last question. Is uncertainty analysis a prerequisite for better calibration? I actually realize now that in the breaks, when I had discussions with young PhD students or just fresh graduates, there's no topic that I've discussed more with people here at this conference than this. So something's brewing. Everybody is working on calibration, apparently, and moving to Bayesian calibration. And as you know, we have done quite a bit of work on that in recent years as well. But here's the point. I don't very much believe in calibration per se. It's a very tricky thing. Most of the deterministic calibration is naive art, and Bayesian calibration is subjective realism. You know, we're tweaking the outcome in a way that we sometimes even don't realize. And to quote a good friend of mine, just to be safe, I suggest you do both. Okay, those were my 10 questions with my own answers. I'm sure you have better answers. So let's make quickly a couple of concluding observations. So I think the fidelity discussion has become more focused. That's good. I also think that if we look at the collective work of this community, our uncertainty quantification, the repositories, the platform to do the mechanical stuff has become very mature. So I think we're now ready for a concerted effort to improve fidelity where it counts. So where we find proof that for certain targets our current tools do not provide the confidence that we need. And I think on the coding, we should, not just for code compliance work, but for other work, stop simulation where it adds no value to the design process. Change the performance gap story. I think I was clear on that. And augment the occupancy variability story. Bring this up to a higher level than this current chasing of the next best stochastic time series. Okay, still a lot more work to do because, you know, this is really what I would like to work on if only somebody would give me the grant to do it, which is not very likely. That we develop these convincing risk cases, go into scenarios, and find with convincing material for practice that our work means something to them. Then we still need to do a lot of work to bring the vanilla repository up to something that we can use for every building. Know where to tweak the vanilla to reflect a real building. And we need to do more work on validation. And then there is this one thing, this barren area in HVAC uncertainty quantification that some of us are working on, still more work to do. So, thanks for sharing your time with me, and hope you see you next time, and thank you.